Since early times, people have had to deal with data and numbers, and have continually sought ways to make this work faster and easier. In the 1600s, Blaise Pascal invented the Pascaline, which could add, subtract, and keep totals. The process of automatic calculation was greatly enhanced by Charles Babbage, who in 1822 invented the difference engine, which would do more complex calculations. Herman Hollerith applied the concept of automated tabulation to the U.S. Census in 1890. The Hollerith tabulator read and stored data from punched cards. Counting dials kept track of totals for each question on the census survey form. First-generation computers were based on the vacuum tube and used plug boards to control the computer's operations. Later, computers used magnetic tape to store programs and data. Eventually, the magnetic disc provided a faster way to access information. Today, common beach sand is used to make the silicon microchips which comprise the processors and memory storage of modern computers.
Now, it's true that from the outside you can't tell very much about how they work at all, but inside, happily, they all have much in common. They all have, for example, the same 5 basic parts. There's that part where information is put into the system. That's called, with considerable logic, the input. The information you put in can come, for instance, from punched cards, or from reels of magnetic tape, or directly from people. Input changes the information into a string of electric pulses, something that computers can handle. That part of the computer where information is put out is called, well, the output. And it does just the reverse, turning the machine's electronic language back into some other, easier-to-read form. Of course, there's not much point in entering information into the system just to get it back again, unchanged. For a computer to do some work, the information must be stored somewhere within the system, in what is known, understandably, as storage. Once safely in storage, it can be sent over to processing, where a variety of logical and mathematical operations can be performed on it. By hooking these parts together, input and storage, processing and output, the system can now process information, but not automatically. That's where, finally, control comes in. Control can operate the other parts of the system, and it can act on a list of instructions worked out in advance. A program. A program is created and placed in storage. Now all the parts are controlled by the program, stored inside the machine. The computer then, in effect, pushes its own buttons. With all these parts and a program, you can deal with numbers at a terrific speed. But taking them all together, you can do a great deal more than calculation. That's because a program can be invented to work out almost any kind of problem. A program is something like a story. Bit by bit, from the beginning, it tells what happens first. And then, for everything that follows, it tells what happens next. And when there's a question or a choice to be made, it tells what happens if. And that can be repeated as many times as necessary. until you get the result you want. Programs may be very simple or very complicated. But with any one of them directing the 5 parts of the system, you have a working computer. And because programs have been written and are being written in almost every field, computers can help people solve a wide variety of problems over the whole range of human endeavor.
A personal computer system may be thought of as a collection of components that work together to do a job. Computer systems consist of 5 parts: people, data, hardware, programs, and procedures. There are many brands and models of personal computers. The Macintosh computers shown here are popular because of their easy-to-use graphic interface. The Macintosh uses the mouse extensively, and the computer is controlled by pointing and clicking to perform various operations. Most computer systems include a printer, and there are many different types. Some Macintosh computers, like this Macintosh Classic, house all hardware components in a single unit with the disk drives and monitor built in. Several types of keyboards are available for use with the computer. These IBM personal computers use a standard operating system called MS-DOS. All computers have the same basic components regardless of the make or model. The central processing unit, or CPU, is the brains of the computer and handles all information processing. Disk drives are included to read the programs and data stored on computer disk, and a video monitor provides a means for the computer to view the computer's output, while a keyboard provides the primary means for input. Software is needed to make the computer perform useful tasks, and fortunately there are thousands of programs available from which to choose. The basis of all modern computers is the microchip. Many are smaller than a fingernail and contain thousands of circuits. These computer circuit boards contain a CPU and ROM memory chips.
My name is Gary Johnson. I'm the supervisor of computer operations here at Texas Tech. We're standing in front of the University Computing Facility, which is a computing resource for the university, at least for the administrative uses. We register students here. We also take care of student records. We also run the financial information management system from this particular computer center. We have approximately 8 operators who work on shifts of 8 hours each, 24 hours a day, 7 days a week. This is the computer operator's console area. From this area, they can monitor the different machines and the different software packages we have going on. They also have a number of reference books to find out what error messages might occur on their screens. Most of the screens are attached to a software package called MVS, and this allows the operating system to run multi-software packages under its protective umbrella. We have 5 printers in here, actually 6 if you count the laser printer, which prints 1 page of laser output, or actually 20 pages per minute. Tape library we have is a combination of both reel-type tapes and cartridge-type tapes, the cartridge tapes being a more new type of technology. We have approximately 6,000 tapes, both on this site and an off-site location. The tapes that we use basically are to back up the disk packs and the information on those disk packs so that in case we have a disk loss, the information can be restored. These platters store the bits and pieces of information that contain the student records and also the payroll records and other financial information that will be kept here on disk at Texas Tech. particular device here is an optical scanner. It scans marks made by pencil on optical scanning sheets. This system's used for students' test grades. We also use it for the payroll system. Each secretary marking the payroll rate and names for the employees. This device is a communications controller. It's the controller that sends signals from modems and personal computers to the CPU and interprets those signals and sends them back to the user using the personal computers. These modems and modem racks allow users who are off campus or who may be on campus using a telephone line to communicate with the computer itself.
The center of the network in the College of Business is a pair of super mini computers, 8 megabyte VAX 750s, that support disk and print services for all of the micros and terminals in the college. It supports administrative applications as well as academic and research applications. The mini computers are loosely coupled. They operate off of a common set of disk storage, about 1.4 gigabytes of disk space, and a tape drive, common disk controller. The super mini computers in the college are located in a standard industrial level computer room with a 12-inch raised floor, air conditioning being driven up under the floor into the bottom of the machines. All cable runs under the floor as well to keep it both protected and to protect operators from it.
Most recently, computers have become a powerful tool to link people together with vast storehouses of useful information and with each other. Working and communicating over space and time. Wherever the various parts of a problem can be clearly defined, the computer can help us manage more effectively. By directing other machines, it can bring about more efficient operation. It can also control processes with infinite precision. And it can increase productivity and offer variety and choice.
In the industrial world, the benefits are significant. To manufacturing, the innovators have brought industrial automation, a new level of quality and performance. For the consumer, it means products with more function at a lower price. Stephanie is 5 years old. She is learning to write and to read with the help of an innovative program fostered by IBM. With Writing to Read, Stephanie and her classmates are putting letters, words, and sentences together, creating stories in kindergarten, a valuable head start in the experience of education.
Sky. The rain is white. I have a cat. It sleeps in my bed.
Listen to the words of children when they've learned something. It's beautiful. They say, now I see it. Now it all fits together.
Welcome to the Education Computer Center at Texas Tech. In this facility, we're concerned with the training of teachers in the use of computers as personal productivity tools and also as a learning medium. Students work with computer-assisted instructions, drill, practice, simulation, tutorial programs. They also use word processors, database, spreadsheet, and graphics programs. We use a system of student tutors in our lab so that more advanced students can help those that are just beginning. Students also use our center for their own personal productivity, statistical analysis, research, writing projects, as well as classroom assignments.
All of the Carroll stations in the college are set up as typing height Carrolls. All the stations have the network available to them for whatever the devices we wish to connect. There's room for approximately 105 workstations in the center, the major piece of which is the room we're in right now. It is a classroom as opposed to a simple lab. It's designed for teaching purposes with an overhead projection system that accommodates a terminal or microcomputer driving the projector. The college supports virtually all kinds of computing applications in the center, from spreadsheet and finance and accounting courses to semantic analysis programs for business communications to compiler languages for MIS, database structures, and so on. The Computer Learning Center can be managed by a single individual working from a central help desk that has the entire center in view from that desk. The networking equipment that actually supports all of the workstations in the college is mounted in the desk.
Desktop publishing began with Apple's Macintosh personal computer and LaserWriter printer. Now, there's a whole family of fully compatible Macintoshes that can give you the power of dedicated publishing systems, but at a fraction of the cost. They connect together easily to build electronic work groups that can even include IBM personal computers. Now, too, there's a new generation of peripheral devices and software of increasing capability and sophistication. Apple's desktop publishing system has become more powerful and more flexible, with the versatility to meet the needs of publishing specialists and general users with equal ease. Macintosh was designed from the start with all the features that desktop publishing requires. A powerful environment for graphics, built in, not an afterthought add-on. The ability to move text and graphics easily from one application to another. A system of windows, menus, and symbols, so you don't need to remember and type a whole set of computer commands. And with Macintosh software, there's a consistency you won't find in any other computer system. Every application for Macintosh works much the same as any other. So you learn new software quickly and transfer your experience with one application to all the others. These are the basic strengths of Macintosh that started the desktop publishing revolution. But that was just the beginning. Now there's a whole new generation with special tools for writers, for artists, for designers, for everyone, with the power to handle book-length work from creation to completion, and the control to make it look the way you want it to.
Robots have been popularized in science fiction movies in recent years. However, friendly and cute androids are more a fantasy than a reality. Robots are currently in the early stages of their technological development. There are two main technical problems which are holding up the further development of the robot: movement and artificial sight. The real robots of 1987 are more likely to take the form of automated mechanical arms which perform spot welds or spray paint on automotive assembly lines than the humanoid creatures of the cinema. Most applications of industrial robots to date involve dangerous or repetitive operations. It now appears that the tinkerers, experimenters, and backyard inventors will modify and advance the cause of robots until someone makes a major breakthrough, which will catch the imagination of the public and find widespread application in schools, the home, and in business. Industrial robots often perform work requiring precision and repetition. These robots can produce the same high-quality work over and over. Someday, robots may be able to cut the grass, wash the dishes, and do the laundry. But today, robots are limited in vision, mobility, and intelligence. Some experts believe that industrial automation is necessary for the United States to stay competitive with other countries. But workers may worry about losing their jobs to automation. Already, some robots can do the work of 6 workers. This chemical lab robot can perform work that is dangerous for human workers. Each task that the robot worker performs is stored in a computer program which controls its operation. Although robots like these hold the potential to improve our lives by doing dangerous and repetitive tasks, many technical and social problems remain to be resolved. This NASA engineer is demonstrating how a human can control a robot arm from a remote location. Using this type of technology, a human on Earth could manipulate objects in space or handle hazardous materials in a laboratory.
Ingenuity and a thirst for innovation brought the computer to where it is today. Inventing and improving computer tools to help people live and work more productively. Inventions like the Thermal Conduction Module, or TCM, radically advanced the art of putting circuits together to make powerful computers smaller, faster, and less expensive. A single TCM can easily handle the information that used to require a room-sized computer. Inventions like the Random Access Disk Drive and cartridge tape system revolutionized the way computers store and retrieve information. Inventions like these can bring the enormous power and speed of large computers even into our homes. We can tap the store of information that flows through financial nerve centers, like the New York Stock Exchange. We can take for granted conveniences like all hours banking, faster checkout lines, making travel arrangements. We have only begun to tap the possibilities. Using innovative techniques, engineers keep squeezing more and more circuits onto tiny chips of silicon. As components shrink in size, computers and associated tools become more powerful and available to more people.
You have 3 messages. Your graduate research team in Guatemala, just checking in. Robert Jordan, a second semester junior, requesting a second extension on his term paper. And your mother reminding you about your father.
Surprise birthday party next Sunday.
Today you have a faculty lunch at 12 o'clock. You need to take Kathy to the airport by 2. You have a lecture at 4:15 on deforestation in the Amazon rainforest.
Right. Let me see the lecture notes from last semester. No, that's not enough. I need to review more recent literature. Pull up all the new articles I haven't read yet.
Journal articles only?
Fine.
Your friend Jill Gilbert has published an article about deforestation in the Amazon and its effects on rainfall in the sub-Sahara. It also covers drought's effect on food production in Africa and increasing imports of food.
Contact Jill.
I'm sorry, she's not available right now. I left a message that you had called.
Okay. Let's see. There's an article about 5 years ago, Dr. Flemson or something. He really disagreed with the direction of Jill's research.
John Fleming of Uppsala University. He published in the Journal of Earth Science of July 20 of 2006.
Yes, that's it. He was challenging Jill's projection of the amount of carbon dioxide being released to the atmosphere through deforestation. I'd like to recheck his figures.
Here is the rate of deforestation he predicted.
And what happened? He was really off.
Excuse me, Jill Gilbert is calling back.
Great. Put her through.
Hi, Mike. What's up?
Jill, thanks for getting back to me. Well, I guess that new grant of yours hasn't dampened your literary abilities. Rumor has it that you've just put out the definitive article on deforestation.
Aha. Is this one of your typical last-minute panics for lecture material?
No. That's not until,
4:15.
Well, it's about the effects that reducing the size of the Amazon rainforest can have outside of Brazil. I was wondering, it's not really necessary, but,
Yes?
It would be great if you were available to make a few comments. Nothing formal. After my talk, you would come up on the big screen, discuss your article, and then answer some questions from the class.
And bail you out again? Well, I think I could squeeze that in. You know, I have a simulation that shows the spread of the Sahara over the last 20 years. Here, let me show you.
Nice. Very nice. I've got some maps of the Amazon area during the same time. Let's put these together.
Great. I'd like to have a copy of that for myself.
What happens if we bring down the logging rate to 100,000 acres per year? Interesting. I can definitely use this. Thanks for your time, Jill. I really appreciate it.
No problem.
Starts with a dream that no one can discourage. To make that dream real, you have the courage. And in all your trying hours, when you're put to the test,